The next speaker, Ghancha Janvi. She is from St. Xavier's Autonomous College, Ahmedabad, Gujarat. She is doing MSc Mathematics. So she is giving a talk on orders for finite non-commutative rings. Yeah, over to Janvi.
So today we are going to find out the possible orders for finite non-commutative rings. Before going into the topic, there are few preliminaries that all of us should be aware of. First, if the additive group of a ring is cyclic, then the ring is commutative. That is, if we have R plus dot as a ring, and if R plus R comma R with the operation addition is cyclic, then the ring is commutative. Second, the fundamental theorem of finite abelian groups. Every finite abelian group can be written as direct product of cyclic groups of prime power odd, and each such representation is unique. Third, if the group is internal direct product of some finite number of subgroups, then the internal direct product of these subgroups is isomorphic to the external direct product of them. And fourth is the characterization of any group of order p square. Any group of order p square is either cyclic, that is, it is isomorphic to zp square, or it is isomorphic to zp internal product zp. And fifth, any direct product of cyclic group is cyclic if and only if their orders are relatively prime to each other. Now the first theorem states that if R is a finite integer of order n, where n is greater than 1, and if n has square prefactorization, then the ring R is commutative ring. Before going into that, I would like to know if anyone can just say me how can we classify integer on the basis of factorizing it. Let's say that I'm giving you an integer 10 and another integer 12. So what are the prime factors for 10 and 12? And how can you differentiate between these integers? Anyone?
For 10, it is 2 into 5, and for 12, it is 2 into
Okay.
2 into 3. So, in the case of 12, there occurs
Okay.
a square of the prime 2. So, n may have a square of their prime factors, or it may have no square. That is, it may be square free prime factorization.
Okay. Very good. So that is what we are going to prove here. If n is any integer that is square free, that is n can be expressed as product of primes where each prime has power p, has power ki, where ki is equal to 1. Okay. So in that case, the ring R is going to be commutative. So in case when we have to show that R is commutative, the first preliminary that I said was that we can show that R with addition operation is cyclic. So we are going to show that R plus is cyclic group. Again, since I have taken that R is a finite ring, so R plus is a finite group. So and any group, any finite abelian, and moreover, it is an abelian group. Can anyone see me why R plus is a abelian group over here?
So by definition, by ring
Why
definition,
can we do that? Okay.
additive, that is a group with respect to addition, right? Abelian group with
It
respect
need
to
to be
addition.
edited.
And in further here,
Any groups?
it is abelian group of
Fine.
square free. Then automatically it is cyclic, right?
Yes. In and the set of cyclic groups, and then we can write it as internal direct product of the cyclic groups. Now, since every CI has it has an order P, where P divides R, but then since R is a square free factor, R has an order n, which does not divide any other primes are in which primes are not repeated. So if order of R is equals to P1 into P2 into P3 up to Pn, so the orders of C1, C2 up to Cn is going to be P1, P2 up to Pn, and each Pi is relatively prime to the other. So C1 internal product C2 up to internal product Cn is a cyclic group. Hence, we have shown that R with which is equals to C1 up to Cn, C1 internal product C2 up to Cn is a cyclic group, and hence R plus dot is a commutative ring. So any ring of order n which has square field factorization is a commutative ring. Okay. So now we are up to next theorem, which says that R has some prime integer, say p, which has more than which occurs more than one in its order. So we are assuming that if p is a prime integer, then there exists a non-commutative ring of order p square. Anyone can say me what are the possibilities of this ring? When I say it as a group with addition, R plus R with group addition with order p square can be characterized as two groups, which is a group of order p square, zp square, which is isomorphic to zp square, which is abelian and cyclic, and group of the group of the form zp cross zp, which is abelian but not cyclic, right? So we are taking R as Zp cross Zp, and therefore it is not cyclic, and therefore we are saying that R plus dot is not a commutative ring. So initially we are taking it as a not commutative ring only. But then we are generating a system for R where A and 0 are the generator for each CP, where A belongs to CP, and the operation here is defined on the form that for every J1, K1A and J2, K2A, the multiplication is defined as J2 plus K2, the integers J2 plus K2 into the first element J1A, K1A. Okay. So the closure property, firstly, we need to show that this ring R with this multiplication operation is this set R with the multiplication operation is a ring. So we are going to show that this is a ring. The closure property is shown here. Let two elements be in R as the set is defined. It can be written as J2 plus K2 times J1A, K1A. And since J2 and K2 are integers, so they can be associated with the first and the second element, and hence we get J1 dash A, K1 dash A, and this element is in R. So we have shown, and the other properties can be verified in this way by the distributive law as the as taking three elements, associativity can be whole, and the what we say identity element is here. Therefore, we have shown that R is a ring of order p square. So we were going to show that there exists a non-commutative ring of order p square. We have shown that this is a ring. Now we are going to show that this is a non-commutative ring. So we will take two elements which do not commute. We are taking 0, A and A, 0. By the operation that we were defining above, can anyone say what is J1, J2, K1, K2 in these two elements? 0, A is an element from the R, and this was the operation that we defined.
J1 is 0.
Yes. K1 is
0.
K1 is 1. For 0 comma A, K1 is 0, K1 is A, and for A comma 0, J1 is J2 is 1 and K2 is 0. Is it easy to see? So by the definition of the operation, J2 plus K2, we have J2 is equals to 1 and K2 is equals to 0. So 1 plus 0 into the first element, 0 comma A. Similarly, when we reverse the two elements, A comma 0 and 0 comma A, we have J2 plus K2 as 1 and this first element is A comma 0, therefore it is A1 into A comma 0, which is equals to A comma 0. Clearly, the two elements do not commute with each other, and therefore R is not a commutative ring. And so we have found a ring of order p square, which is not commutative. So, and p square was, and the ring of, and the order of ring was equal to p square, which means that n is not a square free integer. When we extend this to any ring of order np square, we can similarly show that such a ring is not commutative. Now, by this, I'm not saying that any ring of this order is non-commutative, but there does exist a non-commutative ring of order np square. So we can, so before in these theorems, we have proved that if order of m r is equals to m, and if m is a square free integer, then r is commutative. And if order of m is equals to p square or m is equals to np square, then r may be non-commutative, and therefore with these observations we have the corollary that if m is a positive integer and m is greater than 1, then there may exist a non-commutative ring of order n if and only if m has square factors. So yes, with this we end. Any questions, anyone?
Yeah, so when you are dealing with NP square, what is the multiplication? The same multiplication? How do you define there?
Yes, sir.
Okay,
Since
you
we have
define.
shown that for such rings, two such elements,
Hmm.
this does not hold. So when we are taking cross product of two other of some other ring R1s, R2 say.
Hmm.
So when we are associating that element over here,
Hmm.
say 0 comma a comma 1 and
Hmm.
a comma 0 comma 1,
Hmm.
when we multiply them with the same operation that I have defined over here,
Hmm.
J2 plus K2 plus L2
Hmm.
into the first element 0 comma a comma 1, we will be able to show that the two elements do not commute.
Okay.
We can just generalize this form.
Yeah, this is clear. Now, can you have one more non-commutative ring of order p square? You define this way, right? You provided a counter example. One example you gave, that is correct. You say it is because for every natural number n there is a cyclic group of order n, right? So obviously,
Yes.
when the group is cyclic, additive group is cyclic, then it is a commutative ring, right? But there is a you showed that there exists a non-commutative ring of some order, right? In particular, p square and np square. So, but for that you defined some particular type of multiplication. So do you have other type of rings also? Other type of multiplication, some which is different from this non-commutative ring. Do you have any idea?
No,
Is my question clear?
yes, sir.
Uh, so how do where you got this material? From where you get it?
It is one of the articles
Hmm.
by B.B. Erickson. from
Oh,
Google Scholar.
Google Scholar. Okay. 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 Thank you.